Hello and welcome to the concluding session of Econ 214, part 2 of hypothesis testing. In this session, we'll discuss test of hypothesis for a single population proportion, test for the difference between two population means, and then the difference between two population proportion, and test of hypothesis for small samples using the student's T distribution. This is the outline. We'll test for the proportion, the difference between two means, the difference between two proportions, and then test for sample sizes that are small using the T distribution. Test of the proportion. Now you recall that the proportion is a fraction or percentage that indicates the part of the population or sample having a particular characteristic or trait. So for a sample proportion P, it is X over N, where X is the number of successes in the sample and N is the sample size. We can test hypothesis concerning the population proportion. Now, to test for the proportion, we apply the same 5 steps. You state the hypothesis, choose the significance level, set the decision rule, calculate the test statistic, and make a decision. The test statistic for the proportion, you are familiar with it. You do the Z, calculate the Z as follows, where P is the sample proportion and pi is the population proportion, and the Rn is the sample size. Let's take a very simple example. We want to test the hypothesis of pi equals 0.5 versus pi not equal to 0.5. In other words, it's about testing whether a coin is fair or not, right? You know from our discussion of probability that a fair coin has the probability of a head is 0.5 and that of a tail is 0.5. So the probability of either side is 0.5. If we want to test this at 5%, it means our critical value will be 1.96 because it is two-tailed. And then we'll reject the null if the absolute value of our Z, which is the test statistic that we're going to compute soon, is greater than 1.96. So this is the formula for the test statistic, and then we can substitute the values in it. But let's say that the experiment we conducted, tossing a coin 100 times, we observe heads 60 times. So it means that our sample proportion is 0.6, right? So we will compute our Z, or the test statistic, as this, and we obtain 2. Since 2 is greater than 1.9, we will just reject the null and say that the coin is not a fair coin. If it were, we shouldn't be rejecting the null hypothesis. Let's move on straight away to look at the difference of two population means. Now again, the same 5 steps apply in testing for the difference of two means. So this is how you state the hypothesis. Now there are two means. We want to test whether the two means are equal or not. So you can write your null as mu1 equals mu2, or you can write it as mu1 minus mu2 equals 0, because if they are indeed equal, the difference should be 0, right? So mu1 is the mean from the first population and mu2 is the mean from the second population. Now once you state your hypothesis and then determine your decision rule based on the chosen level of significance, then you compute the test statistic as this. Now note that in this formula, what you will be given is the sample means for the first for the first and second samples, right? But the mu1 minus mu2 essentially goes to 0. So in some cases, you don't even have to report it, all right? And then the denominator is this formula, where S1 squared is this sample variance from the first sample, and then S2 squared is the variance from the second sample. N1 is the sample size 1, and then N2 is sample size 2. Now, the definitions are not here because we previously discussed, and if you see session 9 slides, you'll see the definitions. So let's take an example. A study compared the mean years of service for those retiring in 2009 with those retiring in 2010 at a large company. At the 1% significance level, can we conclude that the workers retiring in 2010 gave more service based on the following sample data? So this is the information. Now we want to call the 2010 as the population 1. So we've given that. So the sample means are 25.6 years and 30.4 years respectively. The sample standard deviations are 2.9 and 3.6, and the sample sizes are 40 and 45 respectively. So all we need to do is to state the hypothesis. Okay? Now the hypothesis says that mu1 is less than or equal to mu2. So either it means that they either 2010 gave the same or less compared to 2010. The alternative will be 2010 being greater than 2009, right? So mu1 greater than mu2. Now, given alpha of 0.01, the z critical should be 2.33. And I'm asking why. You should know why by now, right? So we will reject HO if the test statistic is greater than 2.33. Now, given the information we have, substituting it into the formula, we obtain our z to be 6.8. So because our z 6.8 is greater than our criticals of 2.33, we reject the null hypothesis. And the interpretation is that those retiring in 2010 had more years of service. Okay? Now, if you look at the data, the mean actually for 2010 is greater, but you do not just conclude on the basis of that. Okay? The 30.4 could have been due to sampling variation. So that's why we needed to go through the procedure, and their decision was upheld. Now let's move on to look at testing the difference of two populations. Again, we are applying the same principles. What is important is to know how the hypotheses are stated. And this is how you state the null and then the alternative. Okay? And then this is your test statistic. That's the formula, where pi hat is obtained as the weighted average of the two sample proportions. That's how it is. So you obtain your the pi hat as the weighted average of the two sample proportions. So this is one way in which you can compute the pi. This is an alternative way, because in reality, n1 times p1 is equal to x1, right? And n2 times p2 is equal to x2. Okay, so let's take an example. Now we want to pose this question: are unmarried workers more likely to be absent from work than married workers? A sample of 250 married workers showed 22 missed more than 5 days last year, while a sample of 300 unmarried workers showed 35 missed more than 5 days. So we want to test using the 5% level of significance. Okay, so we want to make the unmarried workers population 1. So we state our null and our alternative as this. Given the significance level, our z is 1.64 or 1.65, or you could also use the average 1.645. So we'll reject the null if z were greater than 1.645. Now we compute our pi hat, it is 0.1036, and now obtain our z as 1.1. Now, this z of 1.1 is less than 1.645. So the null is not rejected. And the conclusion is that there is no difference in the proportion of married and unmarried workers missing more than 5 days of work. Another way is to use the p-value approach, okay, and where the p-value is greater than the significance level, so we do not reject. Now let's conclude our discussion by looking at tests for small samples using the student's t. Now we've already discussed the student's t distribution. We said that it is used in situations where the sample size is small and the population standard deviation is unknown. And the test statistic, as we indicated, will be this sample mean minus population mean divided by sample standard deviation over square root of n. Okay, so this is the example we want to work out. The current rate for producing 5 amp fuses. Okay, so the problem, I will not dwell on it. You can read the problem. But what is important is that we're able to state a null and alternative hypothesis. Okay, now at the 5% significant levels and with n minus 1 degrees of freedom, which is 9, we can read the critical value as 1.8331. Okay, so it is read similar to what we did when we discussed confidence interval, but this time you read for a one-tailed test. It is illustrated in the table as such. So we will reject the null hypothesis if our test statistic that we will compute is greater than 1.8338. Now, our t computed is actually 3.16 based on the data from the question. So, HO is rejected. What it means is that the new machine actually is working faster, okay, it's faster. And as I indicated, you use the table, okay, you use your one-tilt test, and alpha being 0.05, and then 9 degrees of freedom, and read the value as such. Now, I would expect you at this point to solve all the problem sets that will be put at the course website, because it is said that practice makes perfect. This is where we bring our discussion. I wish you all the best in the course. Thank you very much. Bye-bye.